Hello everyone, it's a pleasure to be here today. We will present our work on the Tesla Model 3 that we did for Pontoon Vancouver. Who are we? I present with Vincent Imbert and I'm David Berard. And we did this research with Vincent Dehors. We are both working as a security expert at Synactive in the reverse engineering team. This is not the first time we looked at on the Tesla. We started in 2021 to study the Model 3 by dumping the memory to get the firmware. In 2022, we demonstrated a Wi-Fi pre-auth and zero-click attack chain on the infotainment, and we presented the result at HEXACON2024. In 2023, we did a Bluetooth one-click RCE chain with a Linux kernel LPE and a security gateway ECU RCE. In January, we exploited the cellular connectivity card of the Tesla Model 3, and we chained this vulnerability with an RCE on the infotainment and a sandbox escape. This presentation is about our participation to Pontoon Vancouver this year in April. We used to look at the remote attack surface. So for this edition, we looked at one of the remaining remote entry points on the Tesla. We will present an RCE on one of the Tesla-made ECU called VCSEC. We exploited a vulnerability in the tire pressure monitoring system implementation. Let's speak about VCSEC architecture. The main feature of VCSEC is to do the physical access control. The Tesla application on smartphone can be used as a smart key. It communicates with VCSEC through Bluetooth Low Energy or ultra-wideband. NFC card can also be used to open the car and start it. It's also VCSEC that manages that. One other feature is hosted on VCSEC that is not access control. It's the tire pressure monitoring system that we will detail in this presentation. VCSEC is connected to the vehicle CAN, so it can send order to other ECU on the bus, like open the door. Regarding the hardware, VCSEC is used to be a standalone ECU, but on the last Model 3, VCSEC was included in the VC left ECU, but it's still a dedicated chipset on the PCB. VCSEC ran a PowerPC MCU from ST. It used the variable length encoding, or VLE, ABI. BLE and the ultra-wideband connectivity are not provided by the SoC. For BLE, there are multiple BLE endpoints in the car connected with UART to CAN transceivers. To bootstrap our vulnerability research, we need to have the VCSEC firmware. Fortunately, the firmware is on the infotainment file system. VCSEC is updated by the security gateway with UDS messages on the CAN bus, and the security gateway fetches the firmware from the infotainment. The firmware is split in two parts, the bootloader and the main application, and we only study the main application mode. It's a FreeRTOS operating system, and the application part seems to be developed by Tesla, and they use some standard library. For the reverse engineering, IDA Pro have a good support for PPC VLE, and the decompiler is available. Unfortunately, PPC VLE mode is not implemented in major emulator, so the emulation is not easy. There are multiple useful information for reverse engineering in the ST SDK, like the source code of the FreeRTOS version they used and the low-level drivers. Bluetooth Low Energy and ultra-wideband use protobuf messages. Surprisingly, different features share the same proto formats. So in the Tesla application, there are auto-generated code for the TPMS message handling. Messages are pretty simple. The protobuf message is just prepended by its size. On GitHub, some projects already extracted the proto file from the Tesla application. I'll let Thomas present you the TPMS.
Hello. So I will talk a bit about the TPMS. So TPMS stands for Tire Pressure Monitoring System. And it's used to report real-time information about the tire pressure, temperature, and other information. In Europe, it is mandatory for all new vehicles to have this feature. And you have one for each wheel, on the front, on the rear, left and right. So the TPMS is used to report the status of the wheel to the car and to warn the user if there is any abnormality, like high temperature or low pressure. To do that, in the past, Tesla used radio frequency so the TPMS can talk to the car and know, and for the past 5 years, it leveraged Bluetooth Low Energy, so BLE, to talk to the car. And as we have said before, there are multiple endpoints in Tesla car, and they are used to locate the TPMS position, to know on each wheel it was. And we recently studied the implementation, and at the time it was only using BLE, so we studied the BLE implementation of TPMS. The messages are exchanged over GAAP characteristic of the GAAP service, and for that you have UID that are used for read and write over for the characteristics and to exchange the data. But VCSEC firmware does not directly use the UUID. They use the BLE handle that are only 16 bits. And so we had to implement that. And the data transmitted using protocol buffer of Google. So we study the protocol. And to do that, we used the real TPMS, and we looked at the message it was sending, and we also compare with the protobuf file we had from GitHub to analyze the protocol and understand how it was working. So first, VCSEC connect to the TPMS when the TPMS advertised. And after that, it will send some vehicle information. So this message can contain if the car is locked and if the user is near. And later, when the TPMS is a new one, so when VCSEC encounter this TPMS for the first time, for example, if you changed a wheel, it will it will send a series of specific messages that are required to unroll and adapt. This is called adoption phase or unrolling, and this is only for the first time that the TPMS is seen. And this is important for the rest of the presentation because the vulnerability lies within one of those messages. But usually, in most cases, the TPMS is already unrolled, and so VCSEC will only exchange standard messages, such as tire pressure, the temperature, and other message, as we can see on this slide, where we decoded some protobuf sent from a real TPMS to see the structure of messages. So now we know both about VCSEC and about the TPMS, so we can start looking for vulnerabilities. So as we told you before, the firmware of VCSEC were found inside the file system of the infotainment, and they were not encrypted. But there were multiple firmware. So we had so usually what the smart people will do, they will understand why there are multiple firmware, choose the firmware that match the test setup we had at the time, and start reverse engineering. We did not do that. We picked one random firmware by just picking the one with the highest version. After several days, we found a vulnerability. And the vulnerability was not present in the other firmware. So we were lucky to pick this firmware because if we had picked the one matching the test setup, it would not be vulnerable. So at that point, we didn't know the firmware where it was used and what did this number mean. So we had to understand that. The number is actually the hardware revision of the car. So we asked the vendor, and thanks Tesla a lot, to provide us with the right hardware to test and to know if it was valid for .1. So the version we looked at was the config ID 24, which is actually the firmware for the recent Model 3 of Tesla. It was released since October 2023, and the research started a month or two after. So it was really new, and we didn't have a car or a test setup, but it was actually used. So the vulnerability was in production, and so we were able to confirm that. And also other firmware that we looked a bit at, but the vulnerability was not present. So now that we picked the firmware, we can start reversing. And for that, we used the IDEA decompiler with PPC VLE. It took a long time to reverse because there are many functions, there are no symbols, a few strings, but not a lot. And there are very large structures, and function callbacks are used everywhere. So if you want to track data, you need to do a lot of reversing and spend a lot of time because there are queues that under the message. There are a lot of state machine. So the firmware was a bit complex. But if you just want to identify the entry point of protobuf message, as you can see on the strings, it doesn't take a lot of time. One thing we would like to note about the reversing is that we leveraged the NanoPB decompiler to extract the protobuf from the firmware. And this was interesting because the firmware uses NanoPB, a library for protobuf serialization in C. And we wanted to confirm that the firmware was using the same protobuf as the library, the protobuf file we found on GitHub. And so we were able to confirm that, and also to extract the size of fields, because by default, NanoPB doesn't do dynamic allocation. It's only, so you have to specify the size of each array or repeated field and fix the size at compilation. And so this tool allows us to get the size, and we knew what was the max size for some buffers. And after some time reversing, so we found a vulnerability in X509 certificate in parts. So this message is sent during enrollment or the adoption phase. So VCSEC can ask for the TPMS certificate. And this was implemented in, only for TPMS of type 5. And at the time of the research, no TPMS were in production yet of this kind. So we had to emulate our own TPMS to reach that message. So this X509 certificate in part message is relatively recent. But we don't know exactly why they implemented this message. We suppose that it's for authenticity of the TPMS of the car. If you look at the protocol buffer format, we can see that the certificate is sent using these messages. And this is because the BLE is not made for sending large payloads. So MTU is pretty limited. And so they decided to split the certificate in multiple messages. And so you have only 3 fields. The first is the index of the chunk you are sending. The certificate size is the full certificate size. And the data is the data of this chunk. And as you can expect, the vulnerability is inside the start index, or is due to the start index. There's an integer overflow when checking the start index. And so using a very large start index, you can bypass the if check and reach the mem copy. And as the CPU is running 32 bits with a 32-bit address space. This large value of start index will actually make the destination of memcopy points to just before the start buffer, the certificate buffer. So this results in an out-of-bound write with the destination pointing just before inside the global. So what can we do with that? So we have a maximum data of 120 bytes, 28 bytes, because this is enforced by nano-PB. And if we look at the integer overflow, the start index must be large, but added with the size, it should be greater than 0. So that means that we can overwrite up to 128 bytes before the certificate buffer. And fortunately for us, there is a pointer just before containing a pointer, a function pointer. So this is a structure pointer pointing to a structure that has a function pointer. And this function pointer is used when you send a valid X509 certificate. So just by overwriting this, we can probably get code execution. But let's look at the mitigation first. As this is a small ECU, there's not a lot of mitigation. There is no control for integrity. There is no randomization of ADIA space. And there is no memory protection. So everything is read, write, execute. So that makes the exploitation straightforward. We overwrite the structure pointer using the vulnerability on the left of the figure. Then we craft a function pointer that points to the buffer we control. And during certificate parsing, it will jump to the shellcode. And what's nice about this is that the certificate doesn't have to be signed. The signature validation of the certificate happens just after that function call. And the shellcode, we didn't manually write for PC code. So we use a C code that we compile using the toolchain. And we can also call function from the firmware directly that is used in post-exploit. So now, thanks to that, we have code execution in VCSEC ECU remotely. But the vulnerability is inside the TPMS enrollment message. So we'll let David continue with the rest of the exploit chain.
So the vulnerability Thomas presents you require the adoption of a new TPMS. Until then, we use the UDS messages on the CAN bus to reset the state of a TPMS. And of course, this technique is not valid for Point1. So we looked at the auto-learn mechanism to find a way to adopt new sensors. The car needs a way to adopt or relocate sensors because the user can have two sets of wheels, for example, and users are encouraged to switch the front and the back wheels. So there is an auto-learn mechanism that is run after 90 seconds when the car is moving. As the car has multiple endpoints, it can locate the TPMS position. And if a sensor is not connected during the auto-learn phase, VCSEC tries to adopt new sensor. So we saw that during auto-learn, new TPMS can be adopted. Let's see how to have a disconnected TPMS. To save power, TPMS are disabled when the car is not moving. And when the car starts moving, TPMS are wake up. TPMS advertise in BLE, and the VCSEC handle this advertisement to connect on them if the MAC address of the sensor is already known. When VCSEC is connected, TPMS sensor stop advertising. As you see there is no security to act as a TPMS sensor. You only need to know the MAC address, but we need adoption messages to trigger the vulnerability. We thought that if VCSEC connect to the sensor stop its advertisement. So if we manage to connect on the sensor before VCSEC do, the connection between VCSEC and the sensor cannot be established. and we have a disconnected state for this sensor. This is a race. We need to be quicker than VCSEC. We firstly tried with BlueZ, that is a Bluetooth implementation on Linux, but it was too slow. So we finally implemented the race on ESP32, and we had a good success rate in being faster than VCSEC. With two ESP32, we implemented the denial of service of one sensor and a TPMS simulator that waits for being adopted and playing the vulnerability. So to sum up, first, the TPMS sensor is wake up and start advertising. Then the first ESP32 receive the advertisement and connect to the sensor. So VCSEC is not able to communicate with the TPMS, so the sensor is on the disconnected state. After 90 seconds, VCSEC starts the auto-learn phase. On the second ESP32, TPMS is advertised. So since there is a disconnected sensor, VCSEC connects to the ESP32 and try to adopt it as a new TPMS sensor. The ESP32 sends the TPMS tip 5 in the updater response to reach the vulnerability. And VCSEC sends the certificate read command, and we exploit the vulnerability in the certificate response. And we have a code execution on VCSEC. So to conclude, as a proof of exploitation, we choose to send arbitrary messages on the vehicle CAN bus. It's relatively easy. We just have to locate the function to send CAN messages on the firmware and jump on it with the correct arguments. And here is the result. The exploit worked on the first time at point 1, and we win the car. It was a lot more easier than our previous entries on the infotainment. The infotainment have a good defense in deep with user isolation, multiple sandboxes, memory randomization, and some hardening. So if you want to start a Tesla research, standalone ECUs are a good candidate. Impacts are important since VCSEC is a critical ECU for the car security. With code execution, we can at least open the car and start driving it. We can probably add more smart keys, and having access to the CAN bus can be used to send command to the other ECU. The attack can be implemented on very small devices like the ESP32. And for the fixes, Tesla quickly released a new version, and they also add more checks to other variables. Except this vulnerable command, the code is well written, and we didn't manage to find other vulnerability in the VCSEC firmware. So thank you for listening to our talk. We may have time for a few questions.